So I guess on this screen most of you can't actually see the authors list, but if you look below the title there's a sort of blurry grey blob, and that should give you some idea of the number of people who have been involved on this project. It's been running now for about 6 years, and it's really been a full attempt to redesign the software and hardware interface for security. So to give you an idea of where we start, does anyone remember these machines?
Yes.
So we'd like to think the PDP-11 is this historical machine from the dim and distant past, but unfortunately the PDP-11 strongly influenced the C abstract machine, and as a result we got into this spiral where people would write code that assumed something like a PDP-11 and they would write it in C, and then hardware manufacturers would say, we have this big body of C code that assumes a C-like abstract machine, so what we'll do is we'll make a really fast PDP-11. And then things start to get a little bit confusing when you try and have a really fast multi-core PDP-11 with vector units. But still today, the fastest chips you can buy, the abstract machine that they expose is basically a very fast PDP-11. And this is not ideal because the PDP-11 was a real simplification on a lot of the machines that went before it, and so it introduced entire new categories of bug that just didn't appear on some of the larger machines. And this is still quite apparent. Target managed to get vast numbers of credit card numbers stolen as a result of a memory safety violation. The Heartbleed vulnerability that hopefully people still remember came from overrunning the end of a buffer, something that many earlier machines than the PDP-11 wouldn't have suffered from, but which is just implicit in the model that you get with the PDP-11. And in 2012 there was a survey from Microsoft Research which found that the same kind of vulnerability, the same kind of bug is responsible for 82% of exploited vulnerabilities. And that's really, if you can get rid of all of those in one single fix, then that really reduces the attack surface for any modern programs. And of course, the obvious answer to this is, well, this is a C problem. We have better programming languages than C. We should just rewrite all the code. And that, lots of people would like that. How many people here write C or C++? How many people write in some high-level language that has memory safety? So, 50-50. This is a graph actually from a couple of years ago now, which is looking at the number of new commits in open source projects from a variety of sources, GitHub and a number of other hosting providers. And C and C++ between them still account for about 40% of new commits going into open source projects. Even if that weren't the case, we have about 8 billion lines of legacy C code, about 3 billion lines of legacy C++ code, and that's only counting open source code. If you look inside any large organization, you'll find enormous piles of C and C++ code that have been developed for in-house use. If you say to people, we can fix all your security problems, all you have to do is rewrite all of that code, they do some back-of-the-envelope calculations about how much that'll cost, and then they laugh in your face, and then they kick you out of the building. So when we started with the CHERI project, the goal was to make memory protection a first-class part of the instruction set. And to do this, we wanted a single abstraction that gave us very fine-grained memory safety, so something that you could use for bounds checking every single thing that has a pointer to it, plus something you could use at very coarse granularities for sandboxing. So how many of you use Chrome or some derivative? Okay, so if you're opening a new web page in Chrome, you get a new process running for each tab roughly, and when you get more than about 20 they start combining them into multiple processes. But they do this because different tabs are, roughly speaking, different security domains, and you don't want some malicious code that manages to compromise one web browser window being able to compromise everything. Unfortunately, that's about as about as fine-grained sandboxing as you can support on modern hardware using process-based isolation, which relies on the memory management unit in the CPU. And this means you can get the granularity of a tab, but often you have much smaller security domains. So if you run Gmail in a tab, someone sends you an image, and your web browser will decode that image, and it'll present it to you. And it'll decode it using something like libpng or libjpeg. I don't know if anyone's looked at the CVE list for those two libraries, but I think they average about one a year that allows arbitrary code execution. But that's fine, it can only compromise one tab. Unfortunately, that's the tab that has your Google login credentials, so it can install a malicious version of your internet banking application on your Android device. And it has all of your password reset emails and, all sorts of other things that actually have nothing to do with decoding that image. So what we want to be able to do is support sandboxing at that sort of level of granularity. Decode one image, that goes in a sandbox. Any exploits in the library that is responsible for that decoding can do nothing other than write some data to your output buffer that is not the data that came in the image. And we follow a risk philosophy in this design. So we put mechanism in the instruction set, but we intend to support multiple abstractions at a higher layer. So we try and put as much of the policy in the operating system and in the compiler as possible. And to do this for C, we look at some high-level languages and we steal ideas from them. So we think about pointers, both code and data pointers, so pointers to functions, which are something that are exposed by the C language, but also things that are sort of implicit pointers, the return address that you leave on your stack, for example. These shouldn't just be numbers as they are in a conventional implementation. They should be things that confer you the right to do whatever it is you're supposed to do, but don't confer you the right to do anything else. And this is in contrast with typical C implementations where every pointer is just an integer that you happen to interpret as a memory address. So when I joined the project about 5 years ago, this is roughly what CHERI capabilities look like. CHERI is a capability-based architecture, so it extends the normal register file with a set of additional registers that can contain one of these values. And they had a base and a length, and they had some permissions. And they also had a type which is used for a mechanism that I'm not going to talk about in this talk, but which allows you to provide opaque references to some untrusted code that it can give back and you can ensure haven't been modified by the untrusted code. Every single memory access has to be via one of these registers. So this is how normal memory access looks on a typical architecture. You have instruction fetch, which looks at the value in your program counter, and that contains a virtual address, and then you use the translation look-aside buffer to find what the physical address should be, and then you do a fetch from memory. And the same thing happens with normal loads and stores. You have a value in an integer register, you use that as a base, maybe you have an immediate value as an offset, and the same translation occurs. So we extend this first of all to say, here are some explicit capability registers. You can do loads and stores relative to these, and you can also put them into, well, I'll talk about that in a second. You can do a load and store via one of these, and when you do, the bounds are checked. So if you try and do a load or a store that's outside the bounds or involves one of the permissions you don't have, for example, if you have a capability that only grants you load permissions and you try and do a store, then you get a trap and this fails. And of course, in the model as far as it's written here, there's an obvious flaw, which is you can still do arbitrary loads and stores via integer registers. So we add two special capability registers, a program counter capability and a default data capability. And all program counter fetches are indirected via the program counter capability. All normal legacy loads and stores are indirected via the default data capability. So you can use just these two registers to do very coarse-grained sandboxing. You can restrict them from having the access to your whole virtual address space to having just, say, a 4 GB window in your 64-bit address space. And then you can run legacy unmodified binaries within that box, and they can't do anything that interacts with memory outside of that region. Or you can modify your code and you can recompile it to be explicitly aware of the capability registers, and then you can access either memory inside that box directly via the legacy instructions or via capabilities derived from your default data capability, and you can access memory outside of that box. And that gives you capabilities in registers, but of course that's not very useful if you want to represent every single pointer as a capability, because you have 32 registers and you probably have more than 32 pointers in your program. So we also protect capabilities in memory by having a 1-bit tag per capability-sized bit of physical memory. And we have a mechanism for supporting this in both commodity DRAM or with custom hardware, depending on how you choose to implement this. But the abstract model doesn't depend on any specific implementation. And this gives us both the coarse-grained sandboxing mechanism and the ability to implement fine-grained memory safety. And the important thing about the coarse-grained sandboxing is that it's not actually enough to create a box. Right? Creating an isolated component within a program is actually a very easy thing to do, as long as that component doesn't want to communicate with the rest of the program. And it's this sharing where it starts to get difficult. So how many people have seen Google Native Client? Okay, a couple of you. So Google Native Client is roughly the state of the art in what's called software fault isolation. And the simple version of it is you have a static analysis pass that looks at all of your machine code and it checks, before you do any pointer dereferencing, have you masked off some values, some bits in your pointer to ensure that it's always within a specific range. And in the original implementation, they used x86 segmentation so that the only property they needed to verify statically was every load and store is via a specific segment register. And if it is, and there's no instruction in there that modifies that segment register, then you know that it's constrained. Unfortunately, accesses via segment registers are really, really slow if the segment base isn't 0 on modern Intel chips. So they had to rewrite it to be a little bit more advanced. And this works really well, and it's a nice thing that you can, a nice property that you can statically verify in your running machine code. But it gets really difficult if you want to say, well, I have this box, but for efficiency, I want it to share some memory with something else, because you can allocate that memory inside the box, but then you don't get any bounds checking within that memory, and the code running in the box has full control over the content. So you can't, for example, say, here is a buffer, you may only read from it, or here is a buffer, you may only write to it, or here is actually some memory that's on my GPU, in some shared memory that I have access to and I have a pointer to, and I have no control over where that goes because my GPU driver tells me where to put it. Please write to it here. So we want a mechanism which allows us to do this fine-grained sharing, but via primitives that exist in the operating system. And, primitives that exist in the language. And so this brings us on to the question of what C allows for pointers. And in conventional implementations, there's a big difference between what the standard says and specifically how things are implemented. The C specification has this notion of an object. And objects are ranges of memory that are either allocated via malloc or are created by automatic storage variables coming into scope, or exist throughout the lifetime of the program as a result of global allocations, or in C11 as thread local globals, which appear and disappear as threads start and stop. Okay, and that's a nice high-level abstraction. You have these objects, they're distinct from each other. There's no requirement in C that you have a linear virtual address space. That's just something that we get from the PDP-11 legacy. And you have things that identify these objects called pointers. And pointers identify an object and a position within that object. you can only create pointers by either taking the address of a variable that you have a name for, or if you already have a pointer, deriving another pointer to the same object by some arithmetic. If you have two pointers and you compare them, and they're pointers to different objects, according to the C specification, that's undefined behavior. And so the C specification has this wonderful section at the end about something called int pointer t. Has anyone used int pointer t? No one. Some of you people had said they'd written C code. Okay, tell me, what does int pointer t guarantee?
It'll be the right size for your system. So your 64-bit or 32-bit will point to integer that size.
Right. So,
Is that the right answer?
So if I have a pointer and I cast it to an int pointer t, is that allowed?
You have what?
If I have a pointer, say void star, I cast it to int pointer t, is that allowed?
Well, you can do the cast if you want. It depends on the compiler. It might format.
Okay, so the C specification, first of all, the thing it says about int pointer t is it's optional and it may not exist. If it does exist, you are required to be able to cast a pointer to an int pointer t and back again and get the pointer that you start with. And that is the only guarantee that exists in the C specification about being able to store pointer values in integer variables and transform them back again. So casting a pointer to a long is either undefined or implementation defined in C. And there's no guarantee if you cast a pointer to a long and then cast the long back to a pointer that you'll get a valid pointer at all. And that's really nice as an abstract machine goes. And so if you want to implement a memory-safe version of C with this set of constraints, then it's actually very easy. There's only one slight problem with it. And that's that if you create an implementation that really takes advantage of all of these, it won't be able to run any C code. And that's slightly awkward because it turns out that one of the main things people like from a C implementation is you can give it C code and then run it. Saying, we have this new C dialect, it's memory safe, but you can't run any of your code, makes them just as unhappy as saying you should write all of your code in Java or whatever the language of the day is. So people do all sorts of weird things with C. Right? Actually, one of the causes of the Heartbleed vulnerability was that OpenSSL had a memory allocator that took memory from malloc and subdivided it and defeated any of the guard page or other mitigations that you might have in your malloc implementation. And people do pointer arithmetic all over the place. You know, they like to take an integer, cast it to an int pointer t, do some arithmetic on it, which the C specification says nothing about at all. And then cast it back to a pointer, and that all should work. One of the early pieces of code that we got working with the CHERI C implementation was TCP dump, which is a particularly exciting bit of code because at a paper we presented at ASPLOS a couple of years ago, we enumerated a bunch of slightly awkward C idioms. TCP dump does all of them, and it does them running as root. And it does them running as root while processing untrusted data. So one of the things that you often see in capture the flag security competitions is people finding a new zero-day exploit in TCP dump and using that to stop the other team monitoring what they're doing just before they launch their attack. And you see this kind of thing. It's slightly depressing how much of the really highly trusted code we have is not just written in C, but it's written in C using all of the unsafe idioms in C. And there are a few obvious problems when you start trying to create a memory-safe version of C. The first one is very simple, right? You have a pointer to a pointer and you store a pointer in it. People expect that if you read it back, you'll either get the new value or the old value. You won't get some mixed invalid value, and a whole lot of really critical code depends on this atomicity property. Now, if you look at some of the current approaches for trying to associate metadata with pointers, has anyone looked at Intel's MPX? So this is Intel's attempt to add memory safety. And MPX uses a page table-like structure for storing the metadata about pointers. So this means you might need, I think, 3 memory reads to find where the metadata lives. And of course, each one of those memory reads is in a different page, so might need a page table walk to find where it lives. And I think in the worst case, you have about 130 memory reads to find the location where you want to put your metadata. And if you're trying to write your pointer value and your pointer metadata atomically with 130 memory reads and possibly some traps for pages not found and operating systems filling in missing pages in the middle, that's not very easy. And the only way you can actually do it is to bracket every single pointer write with a start and end of a hardware transaction. And then you end up with something that is noticeably slower than address sanitizer, and actually still not a strongly enforcing technique. And that brings me on to the other question. When you're trying to add memory safety, are you trying to do it to make debugging easier, or are you trying to do it because you want that as a security property? So in the CHERI work, we really want this to be a security property, which means it has to fail closed. So anytime you don't have valid metadata about a pointer, you have to have a thing that is not a valid pointer. You can't do what MPX allows you to do and say, well, the pointer was updated and the metadata wasn't, so we'll just allow any loads or stores via this pointer. Because as soon as you allow that, you give a mechanism by which people can circumvent the memory safety, and then you can't use it as a building block for security. So one of the slightly annoying things you find in C is memcopy. And if you look at any high-level type-safe language, there's no analog of memcopy. If you want to copy an object, you have to copy it with something that knows what the types are, so it can do any of the operations that are needed to update pointers, maybe increase some reference counts, or use garbage collection read or write barriers as it goes through. But in C, you don't have that. In C, when you do structure assignment, so you allocate a new structure, you assign to it from the old one. Under the hood, the compiler will probably insert a call to memcopy for you. If it doesn't, then you still find that programmers do memcopies of structures that contain pointers manually. And even if you don't do either of those, you'll find that the back end of your compiler actually doesn't know the types it's copying. It's just told, please copy this structure using whatever mechanism is most efficient for your target architecture. And this means that your underlying hardware needs to support type-oblivious copying. So one of the first changes that we made around 2012 was to propagate that tag bit that we were storing in memory to say, is this a valid pointer or is this just some arbitrary data, all the way up through the cache hierarchy and into registers. And this means you can load a value into one of our capability registers, and you'll get either a value that you can use for loads and stores, or some arbitrary data that you can still store out into memory, but you can't use as a pointer. And this means we can implement memcopy, which is a nice starting point for C. There are a few other exciting idioms that people like in C. This is one of my favorites because it crops up all over the place. I think Lisp was actually the first language to use this trick. So this has about 60 years of history, although Lisp only used in the implementation, didn't expose it in the language. But the idea is, you know all of your pointers are aligned on some boundary. And even if they're only aligned on a 2-byte boundary, then that still means that there's one unused bit at the end that's always going to be 0. And if it's always going to be 0, then you can store some other value in it. So you can take your pointer, you can cast it to an integer, you can mask off the low bit. So now that low bit of 0 becomes 1, which you can't really see on this projector because it doesn't like red. And now you have a thing that is still a pointer, but it has some extra data hidden in it. And so this looks like it should be fine and easy to support, but one of the problems with this idiom is even if this is a valid pointer, it might be a valid pointer to the very end of an array, which means if you add 1 to it, you've now taken the pointer out of bounds. So any approach that doesn't support pointers going out of bounds but then coming back into bounds before you dereference them will break any code that does this, which includes some unimportant things like LLVM and GCC and Perl and Python and glib, and of course TCP dump because of everything. Another one that is surprisingly common is to allow much larger intermediate values that are out of bounds. So you have a pointer and it points to the start of a buffer, and you have another pointer that starts to the end, and you have some user-provided value. And you add that user-provided value to the pointer, and now the pointer's out of bounds. But that's fine because you say, is the pointer greater than the end? And if it is greater than the end, you bring it back into bounds. And the great thing about this is really someone trying to do bounds checking in software. And it turns out to be tremendously embarrassing if you add bounds checking in hardware and it doesn't work with code that does bounds checking in software. So again, this is the sort of thing that you have to support in C if you want to have a memory-safe environment that still actually works with valid C code. And you want to make sure when the pointer is out of bounds like this, you can't dereference it, but you still should be able to represent it. The last one of these idioms I want to talk about is, I think it comes from FreeBSD, but it's in the Windows NT kernel, it's in all of the BSDs, and it's in Linux in various forms. And it's also in a bunch of user space libraries. And this really comes from the fact that C doesn't have any way of defining generic types, and it doesn't have any kind of subtyping. So the obvious way to define a list in C is you define a structure that is a list of structures containing nothing, so it just has a next pointer. And if you want to use it, you just embed this structure in your other structure. Okay, so now you can walk along this list and you can get the pointer to the next list and the pointer to the next list and so on. But then you want to take your pointer to list and turn it back into a pointer to the containing structure. And this is all fine to do if you are correct in knowing what the type of the enclosing structure is. And you do this by saying, what is the offset of this field within this structure? And that's statically known at compile time, so that's, again, just a number. You subtract that number from this pointer, and then you get a pointer to the start of the structure. And then you say, okay, and now we're going to reinterpret that as being a pointer to the enclosing structure. And that doesn't work if you try and aggressively restrict the bounds. So this doesn't impact our hardware, but it does impact how we design the compiler. And again, in the Intel version of GCC supporting their memory-safe target, if you took the address of the list field, you would get a pointer whose bounds were the bounds of the list field. And when you try to cast that back into the enclosing structure, you'd get a trap, because you're not allowed to do that. It's out of bounds of the address of the field. So we make a decision in our abstract machine that the only bounds that are set automatically for you are the bounds of the object as defined by the C specification. So if you allocate an array, your pointers within that array will always have the bounds of that entire array, and the same thing with the structure. Now, that doesn't preclude you as a programmer from tightening the bounds. You can say, I have a pointer to this element in an array, and I actually want it to only be the width of this one element. But the compiler will never do that for you. So we have really two ideas that we're trying to merge. On the one hand, we have capabilities, and capabilities are an unforgeable token of authority. And our memory capabilities are monotonic in their length and permissions. So you have a capability, you can say move the base up or move the top down. You can say remove these permissions, but you can't ever extend it from this token that you have. And they grant you rights to access bits of memory, as well as identifying them. And on the other hand, we have a notion of fat pointers that's very common in a lot of the memory checking literature. And these are things that describe a point and they add some metadata about it. So we take these two ideas and we merge them together to give us things that are fat pointers, but they're unforgeable and they have very strong security properties. So the end of this gave us a slightly modified representation of our capability, which shrunk some of the field slightly and added an offset. And the offset is what allows you to define not just a range of memory, but a point within that range or outside the range. This is the 256-bit version. We also have a compressed representation, which is only 128 bits, which it turns out when you go to hardware vendors and say, we want you to add 256-bit registers, they look at you as if you're a crazy person. And then you say, we could make them 128 bits, and then they look at you as if you're just a slightly cruel person to their microarchitects. We only apply the checks on dereference. So we allow the offset to wander out of bounds. We allow you to pass these things around with no permissions. And we only check that you have a valid capability when you actually try and use it. So this gives us a continuum of possible implementation strategies. On the one hand, we have pure MIPS code, so our base ISA is a 64-bit MIPS processor, but the set of extensions could apply to any RISC-like processor easily, or to something like x86 with a bit more thought. And in that case, we get no fine-grained memory safety, but we can still run it in a sandbox. We can still take a library and prevent it from having side effects that affect the rest of the program. Then we have our hybrid world, where we have the classical ABI, where most pointers are integers, but we also allow specially annotated pointers to be represented as capabilities. And then at the far end, we have the safest version, where you just take your C code, you recompile it, and now every single pointer in your source code becomes a capability in the binary version. And this means any out-of-bounds memory access will trap. You get very strong temporal memory safety properties. It turns out when we started working on this, we thought this bit will be really hard and this bit will be really easy. From our more recent experiments, we've actually found most code we can now just recompile and it works, and maybe if it does memory allocation or something very low level, we need to make some very small modifications. The difficulty comes in the hybrid code, and there are all sorts of interesting corner cases in the hybrid world. So here are a couple of examples. This is the annotation that says, please represent this pointer as a capability. This one doesn't have the annotation. So if you compile it in hardware mode, this will be a 64-bit integer. This will be a 128 or 256-bit capability. And now you say, please cast from this integer representation to the capability representation. Or you try and do the cast in the opposite direction. And the first question is, well, what happens if this integer is 0? So in our initial implementation, we just took our default data capability and we set the offset to whatever this value was, and we gave you back the result. And that sounds fine, right? Because now you have a capability that can always do the same access that the previous pointer could do. Except that if you do this with null, now instead of giving you a capability that grants you no rights, it gives you a capability that grants you all rights, which is generally the opposite of what people mean when they talk about a null pointer. We also have some corner cases about what happens if you're now in a sandboxed environment and you've restricted the range of your default data capability. What happens if you're doing the cast in this direction, but there actually isn't an integer which you can use relative to DDC and still access the same objects? So we had to add new instructions to handle these casts and correctly handle all of the strange corner cases you get. It turns out the version of this one was also became the cheapest way of materializing a null capability, because you could do a capability from pointer instruction with the 0 integer register, and then you get your null capability. But when you're in this legacy hybrid world, it turns out to be a lot more tricky than you'd first think to incrementally add memory safety. So I just want to finish up with a few of the lessons we've learnt. One is, it was really easy to design the first version of the ISA, and the first version of our C abstract machine worked sort of okay, but we didn't find most of the problems with it until we really started compiling a lot of C code. So the milestone a couple of years ago, we were able to compile all of the C code in the FreeBSD base system in our pure capability world. That was sort of the point where we thought, okay, it is possible to write large amounts of non-trivial C code that actually work with our abstract machine. The other thing we've learned is, well, aside from the fact that I think every single benchmark that I've looked at has undefined behavior somewhere on the hot path, and therefore gives you slightly meaningless results, most benchmarks have been run on a load of different architectures. They have been somewhat cleaned up so that they actually don't really do too many unsafe things. And while they might be representative of real-world code in terms of instruction mixes for measuring performance, they're not very representative of real-world code when it comes to measuring all of the dangerous things people do with C. They tend to they tend to avoid a lot of the idioms that are particularly bad in C. And part of the reason for that is benchmarks tend to be code that is intended to run very fast. And code that is intended to run very fast tries to give hints to the compiler so that the compiler knows how to optimize the code. And when you start straying closer to some of the more awkward corners, you get into bits of code where when you start to run compiler analyses, they say, actually, I can't say anything useful about this code, so probably best not to transform it. And with that, I think Seven is at the back telling me I'm running out of time, so thank you.